Okay, so hello guys. In this video, we are going to solve this problem. So the problem states that a satellite of mass m, a satellite of mass m is moving in a circular orbit around an spherical planet of radius r, and an asteroid of equal mass m falls radially towards the planet, starting at zero velocity from a very large distance. The satellite and the asteroid collide inelastically, and they stick together, moving in a new orbit, such that it just misses the planet's surface. And they are asking us to find the radius of the satellite's original circular orbit. Okay, so in this question, we can first of all observe that just after the collision, the orbit in which they will move will be elliptical, and that elliptical orbit will just graze the planet at this point, as it's shown in the diagram. Okay, and okay, so first of all, what we can find here, first of all, let's assume that u0 is the orbital velocity of the satellite, and u1 is the velocity of the asteroid just before it collides with the satellite. Okay, and u0 and u1 can be calculated very easily. U0 can be calculated by equating the centripetal force to the gravitational attraction pull, and u1 can be calculated by energy conservation, and their values will come out as given. And let's assume that just when it grazes the planet, its velocity is vt, or velocity, tangential velocity is vt. There will be no transverse velocity, as you can clearly note. And okay, so now by angular momentum conservation, we can observe that 2m times u0 times, sorry, I'm sorry, 2 not 2m times u0 by 2, because just after the collision, by linear momentum collision, the velocity of the 2m mass will be u0 by 2 in the tangential direction and u1 by 2 in the radial direction. So by angular momentum conservation, 2m into u0 by 2 times r will be equals to 2m into vt into r. Okay, so from here we can get that vt equals to vt comes out to be u0 by 2 into r over capital R. Okay, now what we can observe that just after during the collision, the energy won't be conserved, but just after the collision and just before it grazes the planet, the energy will be conserved, as there is no external force and there is no dissipative force working, and so energy should be conserved. Okay, so conserving the energy between these 2 points, we can write that half into 2m into u0 by 2 whole squared plus u1 by 2 whole squared minus gm into 2m over small r will be equal to half into 2m into v tangential squared minus g into m into 2m over capital R. Okay, now we just have to solve this to get the value of small r in terms of capital R. Okay, so now we can simplify this as let's cancel 2m from all the parts, and we can get that half will be cancelled, and these 2 will be multiplied here and here. So what we will get, that is u0 square plus u1 square, so 1 by 4 times u0 square plus u1 square, which will give us 3 gm upon r, right? u0 square plus u1 square, yeah, 3 gm over small r, and minus how much, 2 gm over r equals to v tangential square will be u0 square r square by 4r square minus 2 gm over capital R. So and u0 again can be substituted as gm over u0 square can be again substituted as gm over r, and what we can get from here is so 3 by 4 minus 2 gives us around minus 5 by 4 gm over small r equals to u naught square is gm over r, so gm r over 4 capital R square minus 2 gm over capital R. Now we can form a quadratic in this and in terms of small r over capital R. Let's assume small r over capital R to be x. So we get here that minus 5 by 4 gm equals to gm by 4 times x squared minus 2 gmx. Okay, and so now this is a simple quadratic we need to solve, and gm can be cancelled over here. Sorry, I didn't cancel it earlier. And so here we get that x squared minus 8x plus 5 equals to 0. So this gives us that x equals to 4 plus or minus root 11. The negative root 4 minus root 11 can be eliminated because we can clearly see that small r will be greater than capital R. So here we get that x or small r equals to r times 4 plus root 11. So yeah, this is the final answer, and as it was asked in the question, so alpha will be 4 in this case. Thank you.